a couple of series, or a couple of parallel circuits in series with each other. Now, I drew it slightly differently, I just kind of did it this way. But the truth is, isn't that just the same as drawing it?
Drawn on the paper?
Isn't it just the same as drawing it this way? Which is what we had before.
Yeah,
They're all
they're all
common,
connected together, right?
right, with no loads between them, so. So it looks like, well, we've got one thing we might wanna do. We might wanna get rid of the K, right?
1200 ohms instead of 1.2.
Hopefully all of you did that. Change the K, drop the decimal place, add a couple zeros. Okay, we can do that. Then we can actually do some solving here. And in fact, we can solve across for here. But can we do anything before we do any math?
Can't you put the voltage for R1, wouldn't that be on R2 as well?
Based on whose law?
Parallel.
Parallel's law.
And the same thing for R3 and R4 as
Kirchhoff's
well.
law. Yeah,
It's a
Kirchhoff
vodka,
says the voltage drop across two parallel paths is the same. Okay, so Kirchhoff, one of Kirchhoff's laws. So yeah, theoretically, 1 and 2 are gonna be the same.
Yeah. And the same for 3
Okay, and
and 4.
then these will be the same. And then,
Which means you got total voltage there.
what's another one of Kirchhoff's laws?
Voltage is added to current.
Didn't Kirchhoff say that the sum of all the voltage drops in a series
It's gonna
circuit
be 0.
It's zero.
was gonna equal to the source
Source
voltage,
so
Oh, yeah.
right?
24.
that means
So since we've got this being the same for each, in series with this being the same for each, in essence, this component and that component are in series. So the sum of the voltage drops should equal source voltage.
source voltage.
So the first simple layer of math is we could take, one of these and one of those and add them together, and that looks like it gets us
24
to
volts.
24 volts. Okay, so from here, we've really only got, other than a bunch of busy work, we need to solve for R total. And then the rest of it's just doing the math across the grid, right?
There you go.
Yeah, pretty straightforward. So how are we gonna solve for R sub T?
One over.
I figured the total voltage for R1 and R2,
Do we have to do a 1 over 1 over and a 1
Yes.
over 1 over?
and then
So we could say
the
1
sum of
over
those,
680 plus 1 over
270.
270, 1 over, and then we can say 1 over 1200 plus 1 over 560, and then what do we do to interconnect them?
We
Add
have,
those sums
Can
together.
we just add them together? Yeah, so resolve all of that, and you're gonna end up with, I don't know, maybe 1,000 ohms, somewhere in there.
I got 575.07 ohms total.
Is it really that small?
yes,
Oh, yeah, because this is gonna get down below there, so
Yeah.
that's gonna be down in
I got
the,
193 for those two.
yeah, it's gonna be around 200 plus something less than that.
381 as
So,
well.
yeah, okay, so we ended up with, what do we end up with? Survey says 575, 575, 575 point, from there, we should be able to solve it, because you've got 2 ingredients for every column.
Yep.
Right? Okay. Let's hope you, did it well. Let me hand out your, from last week, and then I'll hand out the next one.
I don't know what that means.
Finch, where are you?
Well, that's Ressler over there.
Yeah, you can have that
You
green.
got you two back.
You can have that.
Good.
That's it.
There we go. Kept key. Around, it's still around just a little while. There. Those, yeah. You got that whole point, how you. The row, I'm not sure what happened there, I was trying to figure out something was sideways. Lane. Verse. Scalco. Here. Andrew. Seeing you, not seeing you. All right, so this coming week, 5 resistors. Ooh. That's good though, because that means there's more opportunities for success.
That's
Yeah. Yeah, that's a good thing. Okay. 3, 4. Oh, this is nice. Oh, yeah, looks like we got some series and some parallel.
We're doing, we want to do. Sure.
All right, so let's look at that. So we had just finished talking about inductive reactance. Is that what you guys remember?
Yes.
So a no screen. This is the lost screen. That's not what I see on my screen. You seem to be lost. You have to push the right button. And the right button doesn't want to push. Really? Hey, that's an interesting experience. Okay. So, yeah, I think I had that we stopped right about there. Okay, so remember we said, I don't know what that is. We said because of hysteresis, as a magnetic or as the current tries to increase in a coil, or really anywhere, but it's way worse in a coil. As it tries to increase in a coil, a magnetic field is building, But as that magnetic field is building, it's cutting across the loops that the current is traveling through. As it cuts across the loops that the current is traveling through, it resists the increase of the current flow. So it delays the current buildup. So I'll hook the voltage up, and instead of just going to max current, bada boom, kind of like a light bulb, what's going to happen is it's going to start building up a magnetic field, and the current's going to come on pretty strong at first, and then start getting slower. Immediately start resisting the increase of current. Okay. Once I get up to battery voltage, or whatever the system voltage is, magnetic field stays stationary, current flows at whatever it's at, and the only real thing impeding the flow of current at this point is resistance, right? The heating of the wire. Okay? But until we get to that voltage, the entire time it was building up, it was impeding the current flow. Okay? And to get it to come up, I would have had to work a little bit harder to overcome that magnetism. Same thing when I take and start lowering the current flow, drop the voltage. Magnetic field says, oh, well, I'm going to collapse. And as I collapse, I'm going to start trying to keep the current going because I'm now going the other direction. The way the loops are being cut by the magnetic fields, instead of going this way, they're now cutting that way. So it's going to try and cause the current to stay at its current value, right? So again, it's going to delay that change, that reduction. We call that reactance or inductive reactance. Okay, caused by hysteresis. If we start changing the direction of current back and forth, faster and faster and faster and faster and faster and faster, faster, the rate of change starts increasing, right? Which means the delay gets worse and worse, or the imposition or the impedance gets worse and worse. So inductive reactance, as frequency goes up, inductive reactance gets worse. Inductive reactance as an imposition to flow, just like resistance, follows Ohm's laws. So inductors in series, you sum up all the impedances. Inductors in parallel, you do the 1/1 formula. So you've got to do it for both the induction part, inductive reactance part, and the resistance part. Okay. However, how you interface the two is a little different because of the effect that inductive reactance is having on the circuit. Okay. Okay, so there's a second kind of reactance. We've talked a little bit about what a capacitor is, right? We've said that if I take a pin that works, if I take a battery and I have a lead that comes out here and a lead that comes out there, and they just sit there, one side's going to be positive, one side's going to be negative, right? Well, it turns out that just like a magnet, if I take a magnet here and a magnet here, they sort of don't notice each other that much. But as I get them closer and closer and closer, they either start pulling towards each other or pushing away from each other. And the closer I get them, the more this magnetic field has an effect. Even a fairly weak magnet, man, you get in close, it's hard to get them to, they always want to hit something, right? Okay. Well, the same thing is true with respect to the electrostatic field that exists between a whole bunch of electrons and no electrons. Okay. As I get them closer and closer and closer, what will happen is, it's instead of magnetic fields, the static fields or ionic fields will start getting more and more intense. The other thing I can do instead of moving them closer is increase the voltage potential between them. But what's going to happen is those that the charges that exist with all the electrons and no electrons on this side, that's gonna start causing a bunch of, a number of electrons in the gap that exists between them, which we call a dielectric. That's gonna cause, some of those electrons to also sort of bias, okay? So all these electrons here and none there, they're gonna cause them to bias inside this dielectric. Of course, as I get closer and closer, or increase the voltage, the more intense those fields can interact with each other, just like magnetic fields. And that's the same thing is true with an atom. The closer the electrons are, the more tightly wrapped they go, etc. Now, the problem is with this is I can't fit very many electrons there. Okay? But if I take and make a big parking lot, now I can fit a whole bunch of electrons. Right? And I can have a whole bunch of electrons here. The problem is, once I turn this circuit on, okay, let's say I have a big switch here. We'll put a switch here. Nothing's happening. Voltage is the same across both sides to close the switch. Right? Well, what's going to happen is because they're so close to each other, the battery is going to conduct current for a while. And if I put a load in here, let's put a light bulb in there. This thing, and we're going to say, let's say negative and positive, doesn't really matter. When I close the switch, a whole bunch of electrons can come out of here and park here, and the static force, because these are so close to each other, is going to push all the electrons out of here through the light bulb and back into there. And the light bulb's going to go boom, and go out. So when I first turn it on, we're really not talking DC, are we? What we're talking is a pulse from a DC source, but it's a pulse. And once you get up to the voltage potential across here, to where I now have, let's say it's a 12-volt battery, I now have 12 volts across here, current's going to stop flowing, and the light bulb's going to go out. The resistance here, or impedance to flow, both in this case, is going to be 100%, right? Infinity. No more flow. However, for a brief period of time, I had very little impedance across that dielectric. The static force, because they were so close together, those fields caused all the electrons piling up on one side to drive all the electrons out of the other side through the light bulb. Okay? So at a frequency of 0, other than that initial pulse, impedance or capacitive impedance is infinite, right? Nothing flowing, it's right? But what if I take and reverse the leads of the battery?
Can they flow the other way?
Well, not only are you going to have a negative charge here and a positive charge here, but you're going to now have reversed the same thing here. So now instead of having 12 volts, I'm going to have 24 volts on 24 volts, sending everything the other direction until they get to equal. Then it'll be 12 volts sending everything the other direction, and then it'll come back down to where this is reverse charge 12, and that's holding it, and the light bulb goes out. Okay, so but for a brief period, energy went right through that capacitor real well, even though the electrons didn't, because of that static force. What if I keep changing it back and forth? Light would go on, off, on, off, on, off. Okay, so it would go from only resistance through complete infinity of resistance to only resistance of the current and the load to complete infinity of the resistance. And the faster I go, the less off I'm going to have, right? And in fact, if I go fast enough, the light bulb's going to stay kind of hot. And in fact, if I go fast enough, the light bulb will stay hot and keep emitting photons, even though to us, to the point that we think it's on all the time, right? So it turns out that with capacitive reactance, The higher the frequency, the better, the more easy energy can travel through the capacitor, therefore the less impedance it has. Now it's resistance, the resistance of the load, the resistance of the switch, the resistance of all the wires, even the two plates, that hasn't changed. You still have to account for that. But in an AC circuit, capacitive reactance drops to zero at infinite frequency, and at zero frequency, it drops to infinity. It goes the other way, it goes to infinity. Completely stops the flow altogether. Okay? So everybody see how we can pass the energy of the electrons to the other side and back and forth. So capacitor will allow for that to occur. All right, so capacitive reactance. It is the opposite with respect to frequency. Now, the other thing that's going to happen is, remember we said in an inductor, I need my pen that doesn't work. I am the human voltmeter. Actually, I'm the human power source now. And I attach it to the inductor. Okay, I now immediately have, what am I today? 12 volts. I am 12 volts. I immediately have 12 volts across that inductor. But because of inductive reactance, it takes a while for the current to build up. So the current is delayed. So while voltage goes high, current is delayed quite a bit, right? In the case of the capacitor, the exact opposite happens. When I first, boom, turn this puppy on, it's got very little resistance to flow. It's like a dead short, man. It goes boom. In fact, the power source will drop very, very low. So voltage, current comes on really, really quickly. And voltage sort of lags behind it. So with respect to the relationship of current and voltage, a capacitor will cause voltage to lag behind the onset of current, and an inductor will cause current to lag behind the onset of voltage. Now we'll come back to that later, because that's really, really important. Okay, so with respect to capacitor reactance, old Ohm's law and Kirchhoff's laws, they can all be applied. We can come up with a formula that's based on frequency, and we'll come back to this after we talk about power generation, but we can come up with a formula that will create a value called capacitive reactance, just like we could with inductive reactance. And that value will be an expression of ohms. And the rules for series and parallel circuits will apply, Kirchhoff's law will apply, etc. There's a caveat though. Because frequency and frequency functions backwards, and it's a little difficult to see, but if I take and put another capacitor here in parallel, in truth, all I really needed to do was just connect there, okay? And I've increased the total capacitive reactance. So capacitive circuits in parallel, you just add them together, okay? And the value of capacitive reactance increases, okay? In series, if I put another capacitor there, what I'm really doing is I'm increasing the depth of the dielectric. And so the imposition in series goes down, it goes the other direction. So capacitive reactances in series, I use the 1/1 formula. In parallel, I use the summation, I just add them together. For inductive reactance and resistance, it's just normal, right? We'll come back to this extensively, work a few problems. Okay. And this is very, very important because it affects AC circuits. It actually affects all circuits. However, in a DC circuit, this thing called reactance drops to 0. So there's a value called power factor, and we'll show you how to calculate that. The value of power factor becomes 1 or 100%, depending on how you want to express it. Okay? In an AC circuit, there's always some value of power factor. I just pushed the button and measured it in this building. Power factor in this building right now is 0.96 or 96% efficient. That means we're consuming 96 units of power, but we're paying for 100 units. Okay? Because there's a little bit of imbalance between these reactances. Now, if I could get the two to balance with each other, I could actually drop it to 0, what we call resonance. But okay, so the reactance of capacitive reactance applies just like Ohm's law for resistances does. The only caveat is that one little backwards thing with capacitive reactance. And again, we're gonna have to dive into how AC is actually created before this completely starts making sense. Because how capacitive and inductive reactance affect the circuit are determined by how current is generated. Okay, and we generate current by orbiting around a fixed point. We could do it other ways, but orbiting a magnetic field around a conductor or a conductor around a magnetic field is pretty easy to do. Okay, we can hook up a paddle wheel, we can hook up a fan, we can hook up a turbine, we can hook up a reciprocating engine, a steam engine. It's pretty easy to spin things around and around. Okay, so we then have to spend a little bit of time studying that before we can come back and model what the impact of these two things are. Okay. Okay, so power generation. So let's see. We have some solar cells out there, and that's a growing industry. We have a bunch of other renewable energy type sources, but they're all fans, wheels, something turning an electromagnetic generator.
Yeah.
So I don't know what it is, 99.9% or 99%, or we're getting more and more of these solar cells out there. But for the most part, electricity made on planet Earth comes from electromagnetic generator. In all of our vehicles, planes, trains, cars, boats, buses, whatever, we're going to use electromagnetic generator because they're pretty easy to make. Okay. It has changed a little bit over the years, primarily because we invented a couple of really cool things. We invented the P-N junction, and we invented the NP junction. Yeah, that really radically changed how we do business in so many ways. Every one of you were fiddling on your desk with something, whether it's your watch, your calculator, your computer, your whatever it is, it worked because of these two things called the P-N junction and the NP junction. Okay? That happened about right around World War II. So it took about 10 or 15 years for industry to change. It really wasn't so much that it took 15 years to sort of reinvent the stuff. It really took that long to invent how to manufacture it in mass production. Okay. Okay, so was kind of basically a couple groups. In the first group, what we did is we just took a motor, an electric motor, which we had already worked out. Okay, an armature, which is the thing that has output. The output is mechanical energy, and it would spin round and round and round in a magnetic field created by an electromagnet. Now we'd have to switch polarity, every time it goes around, or a bunch of times as it goes around. But if we took that motor, applied electricity to it, we could make kinetic energy, rotary kinetic energy. Well, it turned out that if you take that motor and spin it by something like a fan, a paddle wheel, propeller in the wind, or something like that, it will make electricity. So this motor slash electromechanical generator works either way. It converts kinetic energy into electricity or electricity into kinetic energy. Now, neither is very efficient if you're trying to do both with the same object. There are some cases in aviation where we've done that. We call them a starter generator. For the most part, though, we don't because you can fine-tune them to where they work much better as a generator or much better as a motor. But the basic components and the basic ideas are the same. In the second group, we had to invent this new set of technology. The new set of technology relies on being able to condense some matter, some material. Carbon sort of works, silicon works a little bit better. It sort of wants to conduct, so we call it a semiconductor. And we can do some magic with it that will allow it to conduct one way but not conduct the other way. Now, as we start talking about this thing, what you'll see is this thing generates AC. It generates alternating current at all times. If all I need is alternating current, then I don't care about either of these. I just spin it by whatever means I have available and let alternating current come out. If in fact I need DC, or direct current, I have to have some way of causing that electricity that's going this way and turning around and going this way to suddenly become this way, this way, this way, or if I can have several different generators working together but offset a little bit, then I'm getting multiple pulses overlapping and I never really get to stop. Okay? Well, why do you need DC? It turns out you really don't. Oh, except for that darn thing called the battery.
So you don't charge
Okay.
the battery.
Light bulb doesn't care, does it?
No.
Toaster doesn't care. The oven doesn't care. Your spark plug doesn't care. And in fact, in aircraft spark plug systems, we just said, yeah, we don't care. It's AC. The little generator in there called a magneto produces AC. Okay. One pulse goes from the ground to the electrode. The next spark plug in line goes from the electrode to ground. The next one goes back the other way. And if it's an even number of cylinders, they're all sort of stuck doing the same thing. If it's an odd number of cylinders, then it changes each cycle. Okay? All right, so this matters if we want DC. The only reason we really want DC is if we've got a battery. Well, unfortunately, for most vehicles, you got to have a battery because that's how you get it started. And, you could, if you got a nice big noodle out on either side of it, you grab it and spin it and start it that way each time. Not a big deal. However, most cars, boats, etc., they don't have a big noodle out there that you can grab and spin. Okay. Well, they did put a big crank on there, but even now it's kind of hard. So the battery is a good deal. They could have designed it around only the battery gets charged by this DC, but everything else is AC. That would have been a little complicated because you'd had to have two different kinds of generators going on in there. So because of the battery, they just stayed with DC. All the rest of the world said AC. And it was, in fact, that was a big, huge political battle between Edison and General Electric. All right, so we came up with some vernacular. In one case where we took the motor and spun it around, the electric motor, and spun it around to generate electricity, we called that a generator. Where we took this invented technology called a diode or a rectifier, we call those alternators. Now, this was magical thinking. I mean, there's no other word for it. It's magical thinking. No other possible way to describe it. If I want to make an AC generator, I take the brushes and I attach them to two slip rings like this. Nothing else has to change. No parts are different. Spin it around, I produce AC. If I want to convert this to DC, I can run it through one of these little things I was telling you about, a diode, check valve, and cause it to become pulse DC. I don't change this at all. Or I could just move the brushes, change the brushes to, instead of slip rings, I'm going to have some segmented rings. Okay? In the part that's producing the output, it's alternating current in both cases. The part that's doing the output is alternating current in both cases. So to say one is an alternator more than another is an alternator is utterly ridiculous. You know, it's a marketing thing.
So what's the difference between that spool and the other one?
The only difference is this just has an A ring and a B ring that goes and wraps the wire, whereas on this it just comes to either side and they're split in the middle. So there's two half rings.
Two half rings.
It's the only difference. I can make it one way or the other, but the current in here will always be alternating current. Okay. Now the other thing that's sort of interesting, and I say this in the slides, is with respect to this is called a commutator. With respect to the commutator type unit, I need the rotating switch to switch the output every time the AC tries to change in here. Okay. If I don't need that, then it doesn't matter if I make this the magnet and this the output, or make this the magnet and this the output. So what is the rotator or rotor and the stator doesn't matter in the world of AC or in the world of rectified DC, where I use a diode. In the world of commutators type, I do have to use the switching mechanism of these two little rings, or 4 segments or 6 segments or a bunch of segments. So
the more segments you have, the less revolutions you have to do.
well, for pulse, but not for amount of energy. Okay, so so for whatever, we just call them a generator and an alternator, and that's only true if we're converting the output to DC. If we're not converting the output to DC, it's straight going to be AC. We call it a generator. So are you confused yet?
Mhm.
Okay, good. I did not invent this.
Can you just,
We'll come back and talk about how that works.
how come you have a light bulb on there?
Huh?
I wanna see the electric.
Can
you prove that there's current coming out of that?
Not with this one. With this one, I might, although it gets charged up and the field doesn't fire off the light. So I'll probably only get away with it once or twice.
Wow.
Nice.
The same.
This is the same thing, only it's a permanent magnet.
There you go.
Ah,
Fire, baby.
nice.
And it would have done the same thing the other way, and it's just, that's AC. Okay?
I'm feeling better.
Feel better. You didn't trust me, did you?
I'm not buying it.
Faith. Come on, you got faith in me. You know, I never lied. Well, okay, yeah, I would lie to you. I'm a pilot, right? You know?
Lips or not?
Okay. So let's talk a little bit about this. If I take a wire and I rip it through a set of magnetic fields, that wire is going to try and conduct current flow. It's going to force electrons to flow. As I'm pushing that wire through those magnetic line fields, they're going to act like pumps, pushing the electrons in that wire as it cuts through. The direction that I'm pushing the wire through, the direction of north to south, or the direction of the lines of flux, both of those will determine which way the current goes, this way or that way. So if instead of going this way, I go that way, it'll change the direction. Or if I reverse north and south, it'll change direction. It will also always act at right angles to each other. So the magnetic lines of flux, maybe they're this way, the direction of travel is this way at right angles, and the direction of current flow is at right angles to both of them. Okay? And isn't that the same thing we talked about when we talked about the forces on an atom with the electrons traveling around? Direction of rotation, direction of the magnetic field, and direction of the static field. Well, that same 90-90-90 or 3-axis field, it still exists. Okay? So because of that, we can use what's called the left-hand rule for generators to show this. Okay? However, and I'll throw this out there, but then we're going to have to back up because there's two other left-hand rules, which you may or may not remember from DC Electrical. So in the left-hand rule for generators, we're going to say, and I don't know, I'm going to throw this out there. You guys remember it any which way you want. Okay, for me, it's very easy. For you guys, it's a little more difficult. So the thumb is the direction of motion. Well, your thumb is hitchhiking. Okay, so you're moving, right? Okay, so the thumb is the direction of motion. The index finger right here, this is where it gets real easy for me. The index finger goes from me, north, to south. Anywhere else, right?
I saw that coming.
Yeah, it's easy. Okay, the only thing left is the middle finger. That's going to show you the direction of current flow. Okay, so if I'm the wire, I'm the north pole, you're the south pole, this is the wire, and we're going upwards. Okay, the direction of current is going to be that way. Right? Now we're never ever going to sit inside an airplane and figure out, okay, the winding goes and this is where the current's going to come out, right? We're not engineers, we're not going to do that. But you do need to understand why a thing is built the way it's built. So this kind of shows it right here. Okay, north to south, okay, index finger. Motion of travel is the thumb, and the index finger is showing the current direction is going to come out the wire. Okay. Now, there are a couple of other rules. Left-hand rules. There's also right-hand rules. So the left-hand rule, if you remember from DC, for the relationship of magnetism and current flow in a wire is if I have a wire and I hold it, and my thumb points in the direction of current flow, my fingers will model the directionality of the magnetic lines of flux going from north to south. Okay? So if I have two wires where they're going the same way, and now the parallel lines are going the same direction, they're going to push against each other, right? But if they're reversed, they're going to pull towards each other. Okay? So the left-hand rule for a wire helps us determine or establish forces being created, magnetic forces being created around that wire. The other left-hand rule says, instead of this being the wire, my hand is the wire. Okay? And my fingers are showing you the direction of current travel. If the direction of current travel models my fingers, then my thumb will be the north pole of the magnet. Okay. And then what's funny is the pictures I found, I think, are backwards.
Yeah, they were. I didn't want to say anything.
Yeah, they're backwards. So there you go. The internet was wrong.
Damn it.
It's like a mirror.
Hate it when that happens.
Because he's using his right hand.
Huh? Yeah, they use the right hand in both of them.
Keller used the right hand rule too.
Huh?
Is Keller?
It's actually left hand. There is a right hand rule for motors, but for those it's actually left hand. But you know, and if you work through the direction the motor travels backwards, you'll see that it has to be. But that's okay. I'm not ever going to test you on any of this. I do want you to understand the left hand rule for generators and ultimately the right hand rule for motors. That's far, far more important. I just don't want you to, the only reason I'm throwing this out there is so you don't intermix the two, you're not confused. All right, so it turns out that if we take a loop of wire and we'll emulate this, we'll pretend that this isn't a bunch of loops, but it's just one loop going around. Okay? Now, if it's one loop that's going around, current is going to go this way and then this way in the segment right here. This part isn't going to do anything for us. This part right in here, all it's doing is conducting for us. But the current that's going this direction is going to be traveling at right angles to the magnetic field going across. Okay? We'll say, since north is standing right here, we'll say north to south. Right? So we're going to use the left-hand rule. Right? So let's say the motion is upwards. Okay, motion is upwards. North to south, direction of current is going to be that way. Right? Then we're going to get over here. Excuse me, I did it wrong. Motion's this way, direction's that way. Yeah, no, I did it wrong. Yeah. So current is this way here. However, when I get to this side, the motion reverses, but the direction doesn't. So that's where I go like this, right? So now the motion is going down. The current has reversed. It's going that way. Well, if the current's going this way here, and it's going that way here, aren't they adding to each other? So the act of these wires cutting through these magnetic fields are going to push the current that direction, and the act of these magnetic or wires cutting through this magnetic field are going to push these this direction. Both of those, because of the loop nature, are going to add to each other, right? So essentially, I've got a little pump on this side and a little pump on this side. And then if I want some more pumps, I just go around again. And again, and again, and again, and again, and again. So now each wire going through the magnetic fields is adding to this pumping action. This shows the same thing happening here. Now, if I'm in this configuration, what's going to happen is my loop is shaped this way, and as I come back around to here, this rule hasn't changed. Okay? Nor has it changed on this side. So that's relative to this magnetic field. However, my loop is now reversed. Okay, so now the current's gonna go the opposite direction in the loop. Then I'm gonna reverse the loop again. It's gonna go the opposite direction in the loop, and opposite direction in the loop, and opposite direction in the loop. Well, if I switch the leads each time, I'll get the same direction out. If I don't switch the leads each time, I'll get alternating current out. In this part of the loop, I will always have alternating current because of this left-hand rule. Okay? The loop nature allows us to get both energy or work or conversion of kinetic energy to electricity out of this side and out of this side, as they're both transcribing arcs. Okay? The other thing we have to take into account of is there's going to be a point where it's no longer cutting through the magnetic lines of flux, is it? Right here? Okay, the magnetic lines of flux are here. While they're traveling this way, they're not cutting across them at right angles, are they? So there's a point where there is no electricity flow, maximum electricity flow, no electricity flow, maximum electricity flow. So as the output of this is going to constantly be wandering, and it's going to be coming out in what transcribes the values of an orbital travel, okay, which become a trigonometric function. Okay, so as it travels around, it's going to go from maximum to zero to maximum to zero, and the way the way it's going to plot out isn't going to be exactly symmetrical like a triangle. Okay. All right. So, and in fact, as we add, each one of these little pumps, we can say it's an electromotive force. So we add more and more of those pumps by making more and more loops. Then we increase the electromotive force. Given a fixed resistance, current would go up as well, right? Or I could play a different game. As resistance went up, I then caused it to go faster and make more pumping or do a whole bunch of different things. The third thing I can do is I can change the amount of magnetic lines of flux. If I have an electromagnet, can I just turn the current up and have more magnetic lines of flux or less? Now, if I have a permanent magnet, I don't got a choice. If it's spinning around, it's going to produce current.
Is it safe to say that
Nothing is safe about electricity.
well, if you had half the number of windings, would that be half the voltage?
At a given fixed speed and a given fixed resistance, yes.
Okay.
So each addition of a pump will increase the electromotive force or voltage. If the resistance is fixed, then the current has also got to double based on the math of that, right? Now, in the real world, load's changing all the time. Okay? All these yahoos, the sun comes up, they all turn their toasters on. Well, they all turn their air conditioners on, and on and on and on. So the load's constantly changing. So we're going to have to come up with some strategies for addressing that. So we're just going to keep adding more and more loops. And with each loop, we get an increase in voltage or current as desired, whatever we're aiming for. Okay. The reason I say this is one of the strategies that becomes pretty apparently necessary is it's actually strategically makes more sense for most loads to try and keep the voltage constant. And so as we add more loops or change the speed of this thing, we're going to create some automated systems that try to keep the voltage fairly constant. And then as load comes on or drops off, we'll change the amount of current that's flowing. So we're going to have to either slow the thing down or speed it up, or if we can't do that, we're going to have to change the amount of magnetism available. Okay?
They don't just keep it constant and then divert all the extra energy somewhere else? Or no?
In the case of a permanent magnet,
Yeah.
they do, because you don't have another choice. But what happens when you divert all that electricity somewhere else?
It goes somewhere else.
It just magically disappears?
No, it kills somebody.
It goes somewhere else. So it creates heat somewhere else
Right.
or waste energy somewhere else. Okay? Because you're paying in gasoline to make that electricity. Okay? Your gas tank is going down for all the electricity that you make.
That's true.
Right?
Yeah.
So if you don't have to make it, you don't have to waste the gas. Or use the gas unnecessarily. Now, the problem is anytime we use a permanent magnet generator or a magneto, and again, that's another vernacular one. Generator, alternator, magneto. They're all generators. They all produce AC. But, yeah, I don't know where we come up with these magic words. Okay. So, and again, by the way, if I were to just say this thing is spinning and we'll do the Jethro Bodine way of connecting things up, we'll just hook a couple wires up there and check the spinning. After wire, it's going to get pretty wound up, isn't it? I'm only spinning a few times before all the wires are wound up. So I'm going to have to do something to allow some relative motion while conducting current. Okay? That means I'm going to have some slipping going on, which means I'm going to have some friction, because there's going to have to be physical contact between two components of matter. And anytime two components of matter are sitting against each other and there's relative motion, there's going to be some friction, some wear and tear. Well, one of the things we know about reducing the wear and tear, as well as reducing what's called the coefficient of friction, is if you take a really hard surface and a really soft surface and bring them together, they don't have a very much friction. Okay? If you take a really hard surface like diamond and another really hard surface like glass or carbon and silicon and rub them together, man, they grind each other up. Well, the diamond usually wins, but they really grind each other up. Okay? I don't know, you take two soft surfaces, two different surfaces of rubber rubbing against each other. Okay? Or how about asphalt? Asphalt is a fairly soft surface, and rubber tires. Okay, a lot of friction between the two. In fact, we use that because the friction's good. Gives us good traction, right? A lot of friction there. But where we don't want friction, we're going to take a hard substance and a soft substance. Well, in our world, we also need the two substances have to be conductive because we're trying to drive electricity through them. So rubber isn't very conductive. Glass, sort of. Semi. Carbon, okay, not too bad. It's a little bit better than glass. It's really hard. In fact, there's nothing harder. It's so hard, it's hard to get it to actually stick into one solid piece of matter. Unless you super compress it, then it becomes diamond. Otherwise, you kind of got to put some binding agents in there, but it stays pretty hard. Okay, we rub that on a really good conductor like silver. Oh, sorry, too expensive. Another really good conductor, copper. Yeah, not so expensive. It's getting that way now, but or maybe even a little bit of brass. Usually they use copper though. As metals go, copper is pretty soft. Not quite lead. It's definitely not mercury, but it's pretty soft as metals go. And relative to carbon, it's very, very soft. So the downside of the carbon is it's very hard and not malleable at all. It's very brittle. It breaks pretty easily. The downside of the copper is it can gouge fairly easily. So what we're going to want to do is we're going to want to push this carbon surface up against the copper surface at just the right amount of tension. Too much and it wears too fast, okay, because of friction. Not enough, then there's a lot of arcing and it wears because of the arcing. You get just the right amount of tension, then you reduce the arcing, don't increase the friction wear. As well, the carbon, as the carbon tends to wear, it leaves small amounts of powder, and that powder acts as a lubricant. It's a dry lubricant that's conductive because it's carbon. Okay, so what we'll do is we'll make these little brushes and they'll be spring-loaded against, to ride against the little thing spinning around, the commutator. Okay? There's an example of a very big commutator with a whole bunch of segments. The really big brushes go there. This is total pain in the butt to make.
Wow.
Here's the deal. We need to win the war.
All right.
If we don't win the war, everybody dies. I need 10,000 of these units by tomorrow.
Okay.
But no pressure, no pressure.
All right.
Just 10,000 by tomorrow.
Right.
By the way, you don't get to actually see it because it's top secret.
Uh-oh.
In fact, it hasn't even been invented yet. You just have to
Really?
invent it. Then 10,000 by tomorrow.
Whew. Tough. Is that how they did it?
We built 394,000 airplanes in 3.5 years while building a whole bunch of Army helmets, bullets, rifles, tanks, sea rations,
But we knew how to do it.
somewhat.
World War II.
We knew what it sort of looked like in some cases. In other cases, not so much.
World War II.
We had to invent it while we were doing it, as well as invent how we were going to do it.
Really?
On the fly.
Yeah.
When
When you stop and just back up and think about what America did,
24/7.
what they did, and a lot of what they produced is still alive and operating today.
Are you trying to say that the electric motor was not around?
Oh, it was around, but in very, very poor form.
Oh,
Not nearly as advanced as what happened in World War II. But more importantly, prior to this, we could build 10 units a day, 12 units a day, as opposed to 12,000 units a day.
right.
And that part was just
Mind-boggling.
mind-boggling. It would take me several years to build one of those. Okay? I don't know about you guys, maybe you do a little bit faster. But, I mean, yeah. Okay, copper rings, a little bit of carbon. I actually have some of those here somewhere. Had some of those here somewhere. Yeah, there's one I can send around you guys. It's made out of, it's carbon only gets so solid, they can press it together, but it kind of flakes apart. So they use a little bit of a binding agent in there to help hold it together and make it a little bit physically stronger. And in fact, if you look at charcoal briquettes, they're just clumped together and you barely touch them and they fall apart, right? So until you take carbon and really superheat and pressurize it, then it gets very, very dense and holds together really well, and it's called a diamond.
Wow.
Where do they get the carbon from?
Huh?
Where do they get the carbon from?
Dig deep.
Like, no, but what is it? Is it
Dig deep. Dinosaur juice.
dinosaur juice? I don't know.
Okay. Yeah, carbon is. There are some natural veins of carbon, but the preponderance of carbon was some organic life at some point. Okay. Buried under the earth, extreme high temperatures, extreme high pressures, to the point that the hydrocarbon molecule, the hydro part of it, the hydrogen part of it, eventually got consumed and exuded out of it. So the only that's left is the carbon. Then if you super duper heat it for a really long time, under extreme high pressures, nuggets of the carbon will form into diamond structures. But it takes very, very specialized or very unusual, unique circumstances of volcanic activity for that to occur, which is why diamonds are also pretty rare. However, mankind figured out how to make diamonds, and they make tons and tons of diamonds. Only because there's all these other guys who are digging it out and saying, hey, these diamonds are really useful, man. They're really expensive, and we're making lots of money. You can't make any big diamonds. We won't let you. So by international agreement, we don't make large diamonds, but we make tons and tons of diamond dust. Because it's so hard, it's wonderful in saw blades and other industrial processes. So we do make a whole lot of diamond, but only in very small particulate form for abrasives.
Is that process just crushing, I mean.
It's, I don't know entirely, but it's super high heat, super high pressure. I mean, in the tens and thousands of pounds and in thousands of degrees. And wait a long time too, wait a while.
massive.
So is carbon one of those limited resources then?
No, it's not that limited, it's just really hard to make them into diamonds. But carbon in and of itself is kind of like many other materials. It's there's a whole lot of it, just like there's a whole lot of aluminum, but it's mostly in granular form, well dispersed throughout. So you gotta collect a whole bunch of dirt and sift all the bauxite out and then get the oxygen out of it before you've got aluminum.
Yeah.
Well, carbon's kind of the same way,
Hmm.
except for those places where a lot of life has happened, concentrated it into hydrocarbon form, then died, been buried, and actually it's usually not dinosaurs, it's vegetation.
Where would I find bauxite?
But just go out in the dirt, dirt out there.
Really?
Yeah, there's bauxite, small amounts of it. Most of the aluminum on the planet is like most of the silica. It's broken up and in very small particulate form. It's because it naturally does that. It naturally corrodes and breaks up into small particulate forms anyway. So there are areas that are very bauxite rich, and that's where they mine aluminum. Okay, so the loop rotates, the wire is reversed, the current must reverse if we want DC. Doesn't need to reverse if we want AC. Okay, the switching doesn't need to happen. The current will reverse whether we like it or not. Okay, and then I said this, it goes from maximum current output to minimum current output. So if I sort of plot that, sort of say my magnets here, lines of flux are going there. As my wire goes around, right in here I've got maximum flux, and as it's traveling this way I've got maximum current, and here I've got no current whatsoever. Okay. Now of course it might be a little bit easier if we wanted to plot this over time. Let's rotate this 90 degrees so that instead of the magnet being here, let's put the magnet here. Okay, and the lines of flux are cutting along like this. And then if we draw the rotation of this thing in terms of either voltage or current, and here we can say either time or degrees of rotation, either way. Okay, and here we could say either voltage or current. As I'm cutting across the very top, I'm going to have maximum amount of current or voltage flow. So I can say I'm right there. And as I get to here, where there's no magnetic cutting, I'm going to have minimum. Now when I get down to here, I'm going to have maximum, but the opposite direction. So we can plot that down to here. Okay, and then when I get back up to here, I'm going to be back to zero, and then ultimately I'll get back up to there, and that will be one full cycle. So one full cycle, okay, so that could be seconds, that could be microseconds, that could be degrees of rotation. So 0, 90, 180, 270, 360, okay. Now, because this is traveling in an arc, there's a point where I'm getting a lot of travel this way and very little travel that way. Versus out here, I'm getting a whole lot of travel this way and very little travel that way. And on and on and on. So what's going to happen is, as I sort of plot this around, what we're going to find is that this doesn't travel, or this doesn't plot out in what looks like a perfect circle. So it doesn't make a nice clean circle, nor does it make a straight triangle either. Okay? And one of the ways to see this is sort of look at the vector dynamics. let's ask ourselves, this is producing alternating current, it's going back and forth. How do I compare that to direct current? What is the DC equivalent?
No?
Well, first off, I got it going backwards and forwards,
Oh,
but since the light bulb doesn't care, we don't care. So we could just take and flip whatever this is up this way, just for the purpose of modeling it, right? Because the light bulb doesn't care which way it's going. So we could say, we could put that up there, and now we're kind of going this, like that. Then we could sort of lob things off and take the tops and fill in the gaps, right? Okay? And ultimately, we would come to a place that's like 45 degrees, okay? Halfway between maximum and minimum. That's logical, that makes sense, right? Okay, so let's figure out what that value is. Because of this vector changing, I didn't get a very good center, so we'll put the center here. We'll say 45 degrees is right there. Okay? So we've said amplitude is a function of distance on this axis. Okay? So the distance from here to there versus here to there isn't halfway. Because for the first part of this travel, most of the motion has been this way, not that way. It's only the latter portion that it's going to be a whole lot of this way and not much that way. So if you take and measure this distance, let's say this was a unit of 1, okay, 1 volt, let's say, or whatever. The distance from here to where that is at 45 degrees angle is going to be the sine of 45 degrees, or 0.707. If max is 1. So when I get to right here, I'm actually going to be at 0.707, and I missed it. It's actually more about right here, right about there, etc. And if I do this all the way around, instead of getting a perfect circle or a straight line, I sort of get this kind of funny, flattened shape that I'm going to lose it because I ran out of edge there, but it's what's called a sine wave. Now if I look at that 45 portion, flip this up so that it looks kind of the same. What I'm cutting off here and plugging down into here actually ends up being 0.707 of my maximum peak voltage. So if I take my voltmeter or my oscilloscope, excuse me, not voltmeter, and I plug it into the little socket right there, what I will measure from here to here is 167 to 170 volts. And of course, from here all the way to there will be twice that. Okay? Now, if I take my 167 and multiply it by 0.707, what am I going to get? Well, it ends up being about 110, 115, somewhere in there. But we always have sort of vague numbers because
118,
118. So yeah, somewhere in
point
there.
something.
Okay, so if I'm truly at 170, it'd be about 120. If I'm down on the other end, and the reason we have some slight variations is it really depends on where you are relative to the power head.
where did you get the 170 from? Where did you come up with the 170?
That's what the actual peak-to-peak voltage is being driven into the wire.
Coming out of the wall.
What you're told about it is it's 115 volts or 120 volts. What you're actually being told is the DC equivalent.
Okay.
Now the reason we have some slightly different numbers, if you use sine wave calculation, it'll be a little different than what they most commonly use is root mean square calculation. And you often, sometimes your meter will say AC and there's a little RMS there.
Root
That's-
mean squared.
Root mean square, that's what they're doing to calculate, to give you the DC equivalent. Again, we're sort of stuck in this DC world because that's where we started from. So values in AC are converted to DC equivalent.
Well, that's-
Confused yet? Yeah.
Yes.
So this allows us though to model the behavior at any, not only point in time, but any aggregate behavior over a period of time, like one full revolution or multiple revolutions per unit of time. It's kind of useful to know what the DC equivalent is, because now that I have the DC equivalent, can I plug that right into determining power? What's the power when it's going all squiggly like that? Kind of hard to calculate it, right? As opposed to the DC equivalent. Well, that's a fixed number. I can do that. I can plug that in the calculator. Okay. So that's part of the reason we do that. And it turns out that the light bulb doesn't really care if you go slightly over and come back down slightly below, go the other way and slightly over and come back down. It's still aimed at an average power value of 120 volts. Okay? As long as you don't spend a lot of time at 170 volts. Okay? Now the other side is, also with some circuits like light bulbs, they actually don't like too low a voltage either. That causes problems. Okay, so again, this sort of says what I just did. We plotted this on the Descartes projection with the x and the y axes. The y axis is always vertical. The x axis is always horizontal, and the z axis always comes off the plane at you or away from you. Okay. And we use this for a whole bunch of things. I can use the x and the y axis to compare two different temperature measuring systems, Celsius and Fahrenheit. And then use the XY point slope formula to come up with a formula for converting Celsius to Fahrenheit or Fahrenheit to Celsius. Okay? This is where geometry and algebra come together and allow us to create formulas. I can do the same thing with trying to figure out the area of a circle. How do you figure out the area of a circle? It's this big round thing, right? Well, the only thing we know, no, you just invented that, right? Where'd you come up with that? How do you know it's true?
I don't.
You don't.
I don't, you just use it.
Well, I can derive it. I won't do it entirely, but I can show you how it works. Okay? I can take a circle like this and say the distance around here versus the distance to here is a relationship of pi over d, right? Okay? Circumference divided by diameter will give you pi. That's another way of saying it. Well, if I start dividing this thing up into a bunch of triangles, I can calculate the area of a triangle, can't I? Base times height, right? And as I keep dividing this up more and more and more, what's going to happen is this distance is going to get smaller and smaller and smaller and smaller and get closer and closer to approximating, right? And it'll be infinitely small. So on one side of the denominator, I'm going to have the number infinity. I'm also going to have infinity number of triangles on the top side. Well, infinity divided by infinity equals?
Infinity.
No.
1, 1, 1, 1.
1. So it drops out of the equation. So the only thing that's left is pi r squared. Okay? But that's an example of using, some geometric shape to create a model or some formula for allowing us to then use that formula in other things. But we're going to use it to model capacitive and inductive reactance in a bit. Okay? In a bit. We'll continue on with generation. We probably won't get through power generation tonight, but we may. So we'll continue on. So let's stop here. Let's see, take about 10 minutes to check your batteries.